Lep pozdrav vsem, spoštovani gospe in gospodje, dragi gostje, člani ASEF. Pozdravil bom v slovenščini, kasneje bomo pa nadaljevali v angleščini, zato ker ta dogodek snemamo in ga bomo uporabljali tudi za promocijo našega znanja z vašim dovoljenjem, tudi pri ameriških ali pa drugih prijateljih preko interneta. Ampak naj rečem dve besedi. Torej, pozdravil sem v slovenščini. Dear ladies, gentlemen, dear friends, guests, members of ASEF, lep pozdrav, good afternoon. And it's my extreme pleasure that my embassy or our embassy, Slovenian embassy in Washington today hosts the Symposium on Artificial Intelligence. Artificial intelligence, basically magic learning machine, which some sees as a solution and others as a threat to all human activities. Today, it's true, the most advanced AI systems are advancing at starlight speeds, and that's why we gathered here. So the artificial intelligence now is becoming one of the most important part also of our diplomatic work. Namely, we do it under the label of science diplomacy. And I'm very proud that our embassy is and will devote even more attention to this, let's say, special branch of the diplomatic work. And especially in the country, US, United States, that is a leader of the innovation and research in today's world. The artificial intelligence is basically in the center of these scientific activities, or to be more concrete, we are stepping into the world of artificial intelligence diplomacy. Artificial intelligence is becoming an important competitive advantage on a global scale, not just the economic, but it will become also a political advantage, security advantage on a global scale, and also a key factor for the stability of societies. International cooperation, thus, is needed for global policy, legal, technical standardization, and also interoperability of the artificial intelligence. Extremely rapid developments in the AI and other disruptive technologies are revolutionizing scientific research. I'm saying nothing new here, and are being to have a daily impact on our lives. While such technologies provide many benefits and opportunities, they also pose certain risks. Risk of rough behavior in the artificial intelligence will pose serious challenges for the human control, meaning security and safety of the artificial intelligence itself. Global regulation, safety regime, security were, as you already know, also buzzwords on London Artificial Intelligence Safety Summit of governments, also participated by China and US, and leading artificial intelligence companies in the beginning of this month. And AI was one of the most important topics also in the discussion between, or the summit between China and United States, between President Biden and Xi, Chinese President Xi, in San Francisco, not far away. Regulation of the artificial intelligence is of strategic importance, but on the other hand, important is also the right balance between the innovation and risk management. Today's symposium brings together Slovenian experts from leading universities and research institutions in the United States. They will present to us how these technologies are affecting the scientific and research work in the fields of medicine, law, computer science, urban planning, serious games, digital world platforms, astrophysics, and cosmology, including the creation of digital humans in a new digital world. Slovenia might be a small nation, but definitely has big brains also in the most advanced research and the most advanced modern technologies. Artificial intelligence-centered developments and research have been taking place in Slovenia and leaving global footprint for the past half century. So the thing is not new for Slovenians or for Slovenian state. Slovenia is founding member of the Global Partnership on Artificial Intelligence. We also established first research center for the artificial intelligence under the auspices of UNESCO, named the International Research Center of Artificial Intelligence, IRCAI. And the aim is to promote international cooperation and partnerships on the artificial intelligence. On the basis of Slovenian national program to promote the development and use of the AI from 2021, respect for human rights and ethical standards are core principles guiding Slovenia in planning of its national artificial intelligence policy, as well participating in creation of the artificial intelligence policy on the level of the European Union. In Slovenia, we just hold also the first national conference on the AI to stock of the level of the artificial intelligence expertise and in all segments in Slovenia, and also to try to answer the questions how to tackle national and global artificial intelligence opportunities for Slovenia. We do support in Slovenia artificial intelligence education at all levels of formal education. And this is very important. Thus, we conduct already in Slovenia a pilot initiative focused on incorporating artificial intelligence into various learning processes. We just hold international conference of the, and this is very similar to ASEF, of the Asian European Foundation, ASEF, named Classroom Network in Ljubljana, not far away, also this one, devoted to digitalization of learning processes in the era of artificial intelligence. On the AI issues, we are active as a Slovenia also in other multilateral and international forums like United Nations, NATO, EU, OECD, Council of Europe, Organization for Security and Cooperation in Europe, and others. And Slovenia supports, and we are supporters of a human-created, human-centered approach in the AI, supporters of transparency, responsible adoption and use of the AI, with a focus on human rights, democracy, rule of law, inclusion, diversity, innovation, economic growth, and advancing of social benefits, particularly SDGs, Sustainable Development Goals, in the frame of the Millennium Goals of the United Nations. We support endeavors for the artificial intelligence governance, where the application and certification of the AI is monitored. We promote government responsibility of the development and use of the AI in military sphere, with the emphasis on ethical, legal, moral, and technical fields for securing international peace and security and enable functioning of the international law. Slovenia, as a non-permanent member of Security Council from 1st of January, will address the issue of global governance and responsible use of the artificial intelligence also on the UN Security Council discussions on artificial intelligence, especially in the context of international peace and security. We also welcome the US government initiative to have leading artificial intelligence companies voluntarily commit to make development of the AI technologies safe and transparent, meaning safeguarding the models against cyber threats and protecting privacy. Last but not least, I have to mention that in an increasingly fragmented international system that we are faced with today, the EU and United States cooperation is of paramount importance in critical areas of strategic rivalry such as trade and technology. And that is why European Union and Biden administration in 2021 established Trade and Technology Council to strengthen technological and industrial leadership while upholding shared democratic values and bilateral economic relations. Transatlantic collaboration is especially crucial for the governments of the artificial intelligence. The EU and US share key principles and a common vision of trustworthy artificial intelligence, but unfortunately, very divergent interests and different policy approaches have so far prevented a real transatlantic consensus on how to regulate artificial intelligence in order to maximize its potential and to avert risks that it poses. In today's world of many threats to democratic systems especially, I do hope we will get, meaning EU and US, on board soon. In conclusion, I would like to thank my colleagues on the embassy, especially Boštjan. I would like to thank members of the ASEF and also Ministry of Foreign Affairs and Ministry for Slovenians abroad for organizing this event. As far as you know, ASEF is an organization dedicated to elevate Slovenian educational initiatives and fostering connections among Slovenian scholars, educators, and scientists worldwide. And I really do hope that the challenges presented today by the scientists would be of benefit of our country, Slovenia, but also of the United States. Thank you very much, and I wish a fruitful work here. Thank you. Not to forget, I think we have two addresses, very important addresses. One is from Minister of Foreign Affairs, European and Foreign Affairs, and the other is from Minister for Slovenians abroad. And let's have a look.
Dear researchers, dear participants, I'm honored to have the opportunity to deliver a few welcome remarks for today's event, Symposium on Artificial Intelligence, organized by the Slovenian Embassy in Washington together with American Slovenian Educational Foundation. No field of work is immune to transformative power of artificial intelligence. From medicine, law to computer science, artificial intelligence has become the driving force behind innovation and progress. It is not just a technology. It is a catalyst for change, a tool that has the potential to redefine the way we live and work. It goes without saying that AI will revolutionize also diplomacy. At the same time, diplomacy, including Slovenia's, has a major role to play in finding the right solutions for the use, management and regulation of AI, both at European level and in other international fora. Just a few weeks ago, the first national conference on AI was organized in Slovenia. The purpose of the conference was to take stock of the level of expertise in Slovenia in all segments, to establish good cooperation between the stakeholders, and to launch an open debate on how to ensure the necessary conditions to promote research, development, and use of these technologies. Artificial intelligence is a comparative advantage and an opportunity for Slovenia in the global international environment. Today, I urge each of you to share insights from your respective fields on how artificial intelligence is shaping the landscape and, more importantly, how we can collaboratively find ways to make AI work for us. I would like to express my sincere appreciation for the dedication of you, Slovenian researchers who have come together in Washington from all corners of the United States. It is heartening to witness our talented researchers contributing to the development of AI in a country where AI is the front of development. I'm confident that the knowledge and experience gained will be a valuable asset benefiting not only the United States, but also our beloved Slovenia. I take great satisfaction in noting that the gathering we are experiencing today, a showcase of science diplomacy, is orchestrated by my colleagues at the Embassy in collaboration with ASEF. I had the privilege of meeting ASEF representatives in Ljubljana this summer. The foundation is dedicated to elevating Slovenian educational initiatives and fostering connections among Slovenian scholars and educators worldwide. In a sense, they serve as ambassadors not only of knowledge, but also as proponents of collaboration, embodying the spirit of cooperation that transcends borders. I wish you a productive and inspiring event. I know your efforts will make it a remarkable experience for everyone. Thank you for your attention.
Spoštovani govorniki, organizatorji in udeleženci današnje konference, gospod veleposlanik, drage rojakinje in rojaki. First of all, let me sincerely thank the Slovenian Embassy in Washington and the ASEF Foundation for organizing this event to purpose which is to spread the exceptional knowledge and achievements of young generation of Slovenians around the world. The power is in knowledge, and young people are the ones who have the ideas, creativity, and potential to shape a better world. Government's Office for Slovenian Abroad has always been happy and proud to support various study exchanges, scholarship programs, conferences, seminars, and other initiatives that connect Slovenia and the world, and that opens up opportunities for our young people abroad and at the same time helps nurture ties between them and their homeland. And that is why my very special tribute today goes to ASEF Foundation for its role in the global integration of Slovenian knowledge. And at the same time to all Slovenian academics, scientists, researchers, students and other professionals in the USA and elsewhere in the world. You make us proud, you are our best promoters and ambassadors. You make a positive impact at home and abroad and contribute to our common development. Hvala vam za to in nadaljujte po tej poti. Lep pozdrav!
It's time that we delve into how we lay the foundations for AI that contributes to the scientific understanding of medicine and the design of safe and effective drugs. Dr. Marinka Zitnik, an assistant professor at Harvard Medical School and director of ASEF, so also my boss, will enlighten us with her talk titled Scientific Discovery in the Age of AI.
Let me spend just a few minutes briefly introducing what ASEF is. So ASEF stands for American Slovenian Education Foundation. It's a non-profit foundation that was founded in 2014 by Dr. Jure Leskovec of Stanford with the main mission of creating bridges between Slovenians and Slovenian scientists, scholars, intellectuals who live and work in Slovenia with those who live and work abroad. ASEF community has grown tremendously over the last few years. You can see here that the ASEF network currently consists of 90 plus Slovenian professors and leading scholars and researchers in Slovenia and those who work in various other countries. We cover over 35 scientific and professional areas from medicine, technology, computer science, and other sectors. And our members, professors, students work at leading universities around the world. At the very core of ASEF Foundation are fellowship programs, and fellowship programs allow students who are Slovenian students. So at the very core of ASEF are student fellowships that are fellowships offered to Slovenian students in Slovenian universities to go and travel abroad and visit Slovenian professors who work at universities abroad, and then experience how is it to do research at foreign universities, learn new knowledge, and bring that knowledge back to Slovenia. And that kind of, in addition to mentorship and research experience, ASEF provides numerous other educational programs and professional career development workshops for those students in order to really help them create new opportunities for them, as well as bring the knowledge and experience about cutting-edge science and research across different disciplines back to Slovenia. There are two directions to fellowships. So students who are Slovenian students working and studying at Slovenian universities go and travel abroad, as well as students and individuals of Slovenian descent who live outside of Slovenia have the opportunity to get as a fellowship to come and visit Slovenian institutions, Slovenian companies and universities, and spend some time learning about Slovenian culture and heritage in Slovenia. So it's really a way of connecting bridges in both directions. Of course, there are numerous other programs that I will not have the time to cover and discuss today, but you are more than welcome to go to asef.net to learn about other research programs and other opportunities for students as well as for scientists and events and programs that ASEF is organizing. And in many ways, that would not be possible without the generous support of our donors as well as numerous partners that we have at, in the government as well as other organizations and partners that ASEF works with. But let me now put on a different hat, which is, in addition to working with ASEF, I also lead a research group and work as a professor at Harvard University. And we are very interested about asking fundamental questions of how AI and related technologies are changing the way we approach science and particularly scientific discovery and what impact AI has on medicine and healthcare. So how is science being done? So fundamentally, the core of science and research is this principle of scientific method. And this is really a principle that dates back to 16th century, and it's a fundamental, systematic, logical way of how that scientists use to try to understand the complex natural phenomena in the world that we are in. And we are now at the stage where AI has started to fundamentally change the way we think and approach science. AI is already here, as it has been pointed out by earlier speakers, and changing science in two fundamental ways. First, it's changing the way scientists do science. What does that mean? So with the onset of ChatGPT and other chatbots, it's possible to use those new technologies as a way to help brainstorm research ideas, as a way to find effectively new information. And so that makes entire research much more efficient or potentially more connected and integrated. The second pillar is that AI is used and is increasingly providing insights that would not be possible using traditional scientific methods alone. There are numerous examples of that we're seeing in science and biology and related fields. For example, a very big, important breakthrough was that of being able to imagine and predict how different molecules, in particularly proteins, really structure and shape and organize in cells, and do that at a very high atom level accuracy using AI models, which something we could not imagine just a few years ago. Another example in medicine is how AI models are now providing very accurate diagnosis for patients that have rare genetic diseases that are typically missed by frontline clinicians because they simply don't recognize diseases that patients have. And AI here can help shorten this diagnostic odyssey that patients need to go to before they arrive at the correct diagnosis. So numerous opportunities in that space. Where is my group in this area? So our overall vision is to lay the foundations for AI that can help us understand better scientific principles of medicine and ultimately help us understand and develop safe and effective new drugs with the ultimate goal of enabling AI to learn and innovate on its own. So that's a very big vision that we break down into several critical components that entail really looking at data across different scales, from the level of molecules, how they interact in human cells, to the level of interactions in the entire human body, and how the human body responds to these external agents or molecules, candidate drugs that are hopefully designed in such a way that they would be useful and help treat the disease for a broad range of patients and critical diseases for which there are no current treatments. And so let me share a couple of vignettes and give very few quick examples of our recent research in this area. So we are very strongly operationalizing this notion of multimodal generative AI. So this is kind of a mouthful term, but here's what I mean by that. So these are now a new class or next generation of AI models that are exciting and interesting because they can provide reasoning and make predictions by considering a broad range of different types of data. That's what multimodal stands for. And they can do that in such a way that one can develop and train a single model or a single AI model, and that model is very broadly applicable. It can help scientists solve numerous different kinds of tasks and answer numerous different kinds of questions with very little or no required adaptation. So the entire process of doing science is then very efficient. Let me give you one example of such a model that we recently developed. And this model is called TXGNN. This acronym stands for Therapeutics Graph Neural Network. But at a very high level, you can think of it as an AI model that takes as input a description of a disease and a description of a candidate drug, and it will produce a prediction that tells us how likely it is that that candidate drug will treat the disease. And if so, what is the mechanism? How will that treatment actually happen at the molecular level? So that's what the model can do. And the beauty of the model is that it works across an entire range of human diseases. So over 17,000 human diseases that are currently clinically recognized, many of which have no approved treatments. The model can prioritize what are candidate drugs that might likely be safe and effective for those diseases. And we are particularly excited about this model because what it can do is it can solve this problem known as a zero-shot inference problem, which is it can nominate a drug for a disease that currently has no effective treatments. Why is that important? You might be surprised that actually there are only around a few hundreds of real therapies that are FDA approved for human diseases. There are many diseases, over 7,000 rare diseases that have no FDA approved treatments. And so if it's possible to use AI to nominate for the first time what might be good effective treatments for those diseases, that can be really exciting. And we showed that this model has this unique capability. We tested its novel predictions by working with our collaborators from Mount Sinai Hospital in New York City, where we looked into data from 1.2 million patients and what kind of treatments those patients were put on for various diseases that they had over time and how they responded to those therapies. And we correlated that information with predictions that are model-made. And what we found is that those predictions the model made and identified as highly promising corresponded to those that the patients actually showed positive response, which was very exciting. We also tested the model against recent FDA approvals. So we asked the model to make predictions in 2021, then we locked predictions and wait for 1 year, see what are new drugs that have been developed and approved by FDA in the next year, and ask, well, has the model successfully predicted those drugs? And the answer to that was yes. For many recent FDA approvals, the model worked really well. And independently of that, we also work heavily with biologists who are really running experiments in the wet lab and kind of creating and growing cells that are infected with different diseases, and they try to treat them. And we ask them to perform their experiments in such a way that the order of experiments was defined by predictions made by the model. And that led to an order of magnitude improved yield in biological insights relative to what would be possible had AI not been used. So beyond kind of these predictive models, what is exciting is also the generative component of it. And this is really what is driving today's revolution in AI, which is that the models can not only make predictions, but they can generate new designs, or they can generate new molecules, but they can also generate text that you probably have seen in many ways, which then allows scientists to ask questions such as, imagine a scientist who is interested in developing a new chemical compound with certain properties, and kind of the scientist would describe what kind of properties they want a chemical compound to satisfy. That would be passed through this generative large language model, and the model would make predictions and generate information about candidate chemical structures with certain properties. And so we are really taking this principle and scaling it up, working with several of our US-based and international partners to build what we call CureBench, which is a universal AI platform that can match drugs to diseases across all diseases that humanity currently knows. And this is really guided by kind of some of the critical mission by our partners, including Chan Zuckerberg Initiative, with the goal of developing and finding treatments for all diseases by the end of this century. Rare as One program, which really tries to find new treatments for over 7,000 rare diseases that have no existing treatments. And we are using AI to help nominate the treatments for them based on these large language models that then fit into clinical trials that our collaborators at Every Cure are running. This is really a challenging problem because in order for the drug to work, there are numerous things that need to happen at the same time. It must be effective, so it must treat the disease. But there's a very simple way to treat the disease: kill the patient, and you treat the disease, right? So you don't want to you want to treat the disease, but the drug should also be safe. So it should be safe for the patient, but treat the disease. It should also affect the right part of the human body. It should not affect negatively other parts and tissues in human body. So it's a very complex problem to build these predictions accurately. And the way we're approaching is by using not only a single large language model such as ChatGPT, but multiple language models at the same time. We think of them as agents, and these agents actually then have roundtable discussion. They are almost AI scientists. They are presented with a big problem of disease that has no good treatments yet. And then each agent, each language model provides an initial response to what a good drug, how a good drug for that disease might look like. And then this initial response is then refined through multiple rounds of discussions between these large language models, where in the second round, every large language model or agent sees the response of their fellow large language model from the previous round, and they're asked to refine their answer. And they repeat and repeat that multiple times to arrive at a really high quality response that the models that we can then act upon. So I talked a lot about clinical drug development, which is mainly concerned about matching drugs to diseases at the level of patients that interact with the healthcare system. But it's very important to also think about what's happening at the molecular level. And in this particular context, an exciting problem in the field is that of developing virtual cell simulators. That's a very big open challenge, where the idea is, can we develop these multi-model generative AI models that one scientist could use to test very quickly their hypothesis in a virtual manner without necessarily having to go in the lab and design experiments from scratch. So let me just illustrate what would that entail. And I'll use an analogy outside of biology for a moment. Let's look at the word apple, right? So apple is a polysemic word. We can grow an apple, we can buy an apple. And the meaning of the word apple really depends on the sentence within which that word apple occurs. But similarly is going on at the level of cells, at the level of molecules. So there is a gene, H2AFX. H2AFX is now a pleiotropic gene. Seems a very big word for those who are not biologists, but what that means is that the meaning, the role, the function that this gene plays also can change with context. But now that context is not given by sentences or paragraphs, but it's given by biological environments, like groups of cells. And so if we want to have these good virtual cell simulators, we really need AI models that can adjust their outputs based on the context in which they operate, and do that in a very dynamical manner so that predictions are precise. So we developed models like that are contextual AI models that can generate predictions specialized to individual cells and group of cells called cell types that can be very easily and quickly adapted to cell types and cells that were not encountered before in the training set of those AI models. And what those models can do, they can provide precise predictions, which is important for realizing the notion of targeted therapies, where the therapies are optimized for specific molecular signatures that patients have, and they can find what are most predictive cells in a sample from a patient that should be targeted by the therapy, and what are those cells that are most indicative of response of patients to the treatment. we can do that for very important therapies that called immunotherapies that are a pillar of modern oncology. So let me kind of wrap up here by a bit of this final slide of a broader comment of how it is important in order to facilitate broader use of AI in science to bring together very diverse communities. And so to that end, we established therapeutics data commons that serves as a meeting point between, on one end, biomedical scientists, biologists, chemists who know what are the critical bottlenecks of drug discovery and development, who know what are the dangers and risks of potential dual use of these models that can perform chemical optimization, and on the other end, computer scientists, AI scientists who know what are exciting algorithms that one can develop for problems that were identified. And so in doing so, we build bridges across different communities and facilitate both algorithmic innovation as well as responsible ethical adoption and use of models in this field. And of course, all that would not be possible with a group of students, as well as many collaborators and partners that we have to work on our research. So I'll wrap up here. Thank you very much and I'm happy to take any questions if there's time for them.
Moving on, we have Dr. Alenka Poplin, an associate professor at Iowa State University with a background in geoinformation science and an impressive area of degrees. Her talk, titled Serious Geogames and Artificial Intelligence, will explore how AI can transcend mere entertainment, impacting player experience and understanding user behavior through data mining techniques. Please.
Dobar dan, je res lepo biti tukaj na tem delu slovenskem ozemlju, so to say, right? Hvala, da ste prišli in I'm going to switch to English. Welcome to my presentation on serious geogames and artificial intelligence, and the subtitle, The Future of Games is AI, maybe a question mark. So my focus is on serious games. These are games that are developed for more than just fun and amusement, enjoyment, joy, and playfulness, but they are developed to solve problems, help solve problems, and deal with real-world situations. And the groundwork somehow was laid down by Abt in 1970, but talking about games that were non-digital. So I'm focusing here on digital games, online games, and we add geo games for games related to earth and land, and geo coming from ancient Greek word for Gaia. And let me give you just some examples, but before that, when we talk about seriousness and play, we mapped here the prototypes that students developed, and we can see that they can be very playful, and in the very playful there is very little for seriousness, or they can be very serious. And there's very little for playfulness or they can be in the whole range of in between. So we are talking about that range of games. Let me give you some examples. This one, you can see the user interface in the German language goes back 12 years ago. One of the first ideas in urban planning, the question was, can we design a game that will enable urban planners to engage residents in discussions about the future of their cities? And it is a platform, 2D, 3D platform that enables the residents to submit their suggestions for this marketplace. It is in Hamburg. It's a real-world example. And the little monkey that you see here, it's called NPC. This is an expression often used in games for a non-player or non-playable character. And it's any character in a game that is not controlled by a player. And in this case, it just accompanies the player and gives suggestions and is fun and entertaining. And then the second example I can give you is a PhD by Italo De Sena, Geominas Craft game. takes us into Brazil, into Ouro Preto, is UNESCO heritage site. It's a mining site. Ouro stands for gold. And you can see that is also NPC here is the director of the visitor center, and the players can communicate with different NPCs included in the game, and is specially tailored for children and was developed in Minecraft that many children like to play. And so it is a learning game, exploring the enables exploring the biodiversity of the area and the consequences of the mining area on the built environment. The third example, and we go chronologically, this is the more recent example that we worked on, is called E-Footprints Energy Game, and takes the player into a city, into then a neighborhood, and here into a home, into the room. And it's kind of a simulation game where the player can set up the energy, set up the temperature, open up the window. The game invites the player to feel really comfortable. And it is also, additionally to just playing, was developed to study human behavior related to energy consumption. Because if we ask people in a questionnaire, what would you save? Do you want to save energy? Everybody says, yes, of course. So we were searching for alternative possibilities to explore how people behave in a real-world setting. And it contains a back-end data storage where, of course, every decision in the game is stored in the back end, and we are going to use data mining on players' behavior. By the way, probably all the games that you play or you respond to some questions in Facebook, they might be contributing to adding to your profile online. So be aware. They are not just for fun. Okay, now what are the new developments? And I'm looking into technologies, hardware and software that are impacting our thinking, our research in this area that is in the intersection of geoinformation science and urban planning. And one of them is definitely mixed reality. Pokemon, I guess known to everyone, brought $90 billion revenues, one of the most successful or the most successful games, where you have your device and the creatures on your device interact with the physical, you're in the physical world, so it's integration of the physical and virtual world. Why is this so exciting for us? Here you can see the augmented reality glasses that people can put on, and for urban planning, exciting is to understand how, and these objects, by the way, they are virtual, but people can grab them, move them, experiment with them, so the planners can present different opportunities and options for the design and explore how people feel in this created virtual environment, and then give a feedback. Would they like to have a walkable path over there? How does this feel like? The second I would like to mention is procedural content generation. AI generates in an automatic way content that is comes in form of interactive stories. It can come in a form of different elements of games like environment, conditions, different levels, music. And the advantage of that is that the player can get a very interesting new content, and also helps reduce the storage space. An example would be in our footprints energy game. Suddenly we have an extreme heat, or it's extremely cold, and this is presented to the player, and here are other options: turning on the AC or closing the blinds, turning on a fan. And by the way, the different levels, if somebody plays Candy Crush, anybody does? Yes. I don't want to admit, but I do it too. So, of course, they use machine learning to create different levels. And you might not be playing the same game as I do, because we as players have different patterns. And so that is what AI is doing in the background for us. The third interesting aspect is modeling players' experience. We have now hardware and tools like cameras, RealSense, Intel here. They stopped producing this one, but also the biometric feedback that is given by the watches that you might be wearing. Your camera in your laptop might already have a new version of the camera, and you might not even know. But what they do, so what's possible to do, is to measure your biometric feedback, the emotions, your reactions, and by the way, how you click, and not only in games, but also in other applications, to understand what your skills are, what your abilities are, what your knowledge is. And based on this help with the hardware, there is this play between the understanding of the player and then how the game or any other computer system responds to you as a player. So, which is really interesting, because then the game can, there can be a dynamically balancing game difficulty and response in real time depending on the player. Why is this interesting is because we can have one application, one game, but it would appeal to diverse audiences. For example, for urban planning, we might have an application, but it would be played by elderly generation. They would use it in a different way, and then there would be a dynamic, another version offered to Gen Z, for example, right? Right? So, example of that, this is kind of a Nevermind game, 2015. The greatest enemy is the inside of your head. It's almost a horror game. The player is an expert in treating repressed mental trauma. You can see in the middle, this is all the trauma that is coming back. And so, of course, because it puts the player in a stressful situation, measuring the biometric feedback, then the game, the player is under stress, the harder the game becomes, and then certain events occur, like the game screen may become foggy or unsteady, navigation is difficult. In a positive sense, for urban planning, we see really interesting aspects of combining affect, emotion, memory associated with places, and creating 3D environments that kind of help understand which are, for example, places that create positive emotions for people, and how they are designed, and studying design of those places to create more places like that. Another thing I'm very excited about, and you could see in our user interface how visualization got better with 3 games that I showed to you at the beginning. One of our really key research questions was how to visualize the real world as realistically as possible in a game. And this for years, me working with geospatial data, visualizations, 3D visualizations was a very tough cookie, one can say, right? Tough thing to solve. Now we have this development in Unreal Engine 5. You can see here the pictures and examples, Nanite, an engine that allows for high detailed photographic source material to be imported in games, and amazing visualizations that are very, very close to reality. Even photogrammetry assets can be used to create those images. This is also very interesting for our research. You can see here Twin Cities research in urban planning. There is very interesting research that looks into, let's say, Washington, D.C., real-world city, and the twin is a digital twin that is a visualization of Washington, D.C. in a digital world. So the new developments with engines and what games are contributing is the ability to visualize, the ability to realistically visualize the cities. Adding the 5.3, the new version, sparse volume textures like visualizations of leaves and trees, which was very difficult in the past, becomes possible. Additionally, complex simulations, here just example, smoke, fog, explosions, clouds, are becoming really realistic for urban planning, visualizing floods or fires and simulating is additionally exciting. Character animation, very easy in the new engine, but particularly I'm excited about dynamic lighting, global illumination, the ability to, how light is bouncing in real time, and the shades, reflections, true real-time illumination, very interesting. So lots of interesting new tools for urban planning and for games, really exciting. And I'm leading efforts at ISU, Iowa State, out in game design major. I'm really happy to announce that it's in the approval process. It was selected as the degree of the future, and we expect and hope to get first enrollment envisioned they are envisioned in fall 2024, with 3 focused areas: art and interactive media design, game computing, and game words and narrative design in society.
My name is Urska Velikonja. I'm a law professor at Georgetown. I'm also currently serving as Associate Dean for Academic Affairs, which is the academic dean, which means I oversee the law school's very large curriculum and exam administration. And that explains why my talk comes in these 2 parts. A lot of what I do today is dealing with the everyday managing a large organization. Like the speakers before me, I'm not going to talk about what generative AI or even general artificial intelligence could do in a few years. We honestly don't know where we're headed. So instead, allow me to reflect on what the availability of generative AI has meant for legal education and legal practice to date. So ChatGPT, right, the generative AI model that most of us are most familiar with, came out in November, just before fall exams. And you can see how, like, with it brought a fair amount of existential concern for the business in which I find myself, right? We all felt like the wolf is at the door. We were asking each other, like, what are we all doing? Can we ensure testing integrity, right? Late November is the time when we're getting ready to administer exams, which is true right now as well. More importantly, will the profession for which we are training our students still exist by the time they graduate from law school in 2 or 3 years? And so when ChatGPT first sort of really came out, opinion leaders made 2 significant predictions relevant to my discussion today, right? Number 1 was that generative AI would most significantly disrupt knowledge industries and knowledge workers, and would change a lot of white-collar jobs, right? You've heard Marinka talk a lot about how it's changed scientific research, right? You've heard Alenka talk about gaming industry. And here on this list, like, legal services was identified as a discipline that would be among those most significantly affected by generative AI, and the expectation was that this would happen fairly quickly, right? So here's a headline from The Economist. Law would become, the generative AI could radically alter the practice of law. The idea was you could just ask any question you have of the model and it would give you an answer. And if so, law now would become accessible to the masses at no cost, right? ChatGPT could provide you answers. It could draft competent briefs. It might even offer fair dispute resolution. Law firms and the entire legal profession would be put out of business. Okay, so here's another couple of headlines. ChatGPT passes the bar exam. Now, the first iteration, the one that was released late last year, ChatGPT 3.0 and 3.5, failed the bar exam. The one that passed was ChatGPT 4, and I think it was released like in March or late March of 2023. And it not only did it pass the latest version, aced the bar exam with a score nearing the 90th percentile, right? Now, okay, an aside, it didn't. This is not an accurate headline, which is true for a lot of headlines out there. What the authors of the study did, they took the result, the raw score that the ChatGPT program got on the bar exam, and compared it to the February administration of the bar exam. Any lawyers in the room? A little bit? Yeah, so there's two administrations of bar exams in the United States. There's the July administration, which 90% of bar exam takers do. So when a kid graduates law school, student graduates law school, they sit for the first bar exam that is available. Only about 10% of students take the February bar exam, and the ones who take it in February are the ones who had issues during law school. So it's not a neutral pool of students taking the February bar exam, it's those who had issues during law school, or importantly, those who flunked the July bar exam, right? And so what we're comparing is the results of students who flunked the bar exam with ChatGPT, right? And the best predictor of failure on a bar exam is prior bar exam failure, right? And so when you compare the results of ChatGPT with the students who are taking the bar exam for the first time, its success isn't quite as impressive. It still passes, right? It does better than, like I think it was 48%, it's at a 48th percentile of bar exam takers. So it passes because about 2/3 of bar exam takers will pass it, but it doesn't pass it quite as successfully as the headline would let you believe. Okay, that was just an aside. Now, the second prediction that was made is that the existence of generative AI would change education. It would make it much harder for teachers to grade students' papers written with the aid of such tools, right? The second prediction has proven challenging to a point. The first one certainly has not materialized. The law firms are still making the big bucks without the use of generative AI. So the purpose of the remainder of my talk is to look at why has progress been slower than what was initially anticipated? Like, what are some of the challenges addressing some of the concerns that Marinka already raised during her Q&A? So what's going on? Well, generative AI, ChatGPT, is not general artificial intelligence, right? ChatGPT doesn't think. It's a calculator for words or a predictor for words. It's an autocomplete mechanism. It's very powerful, it's very effective, but that's what it can do. It does not understand what it does, but can write text coherently and in perfect English. Great for college essays or high school essays. A little harder at law school. Not impossible, but a little less useful. It hallucinates. It makes up stuff with surprising frequency. And because of all it does is predicts the next word in a sequence, yes, taken into account context, it also makes sort of dumb mistakes. Mistakes that are unusual for like a person to make. It just makes different types of mistakes. The other problem is, right, it relies on the quality of underlying information. When the quality of underlying information is poor, the output is going to be poor as well. These sorts of mistakes, as rare as they may be as a general matter, are a problem in a legal profession where a single misplaced comma will cost you $100 million. Or for our students who are all gunning for a good grade on exam, and they're all like, we're not talking about the median American, we're talking about students who got admitted to one of the top law schools in the country. They're a fairly competitive bunch. ChatGPT was not admitted to Georgetown Law, right? And so what they want to do is to get a good grade, and for them, mistakes, they feel they're just as costly as a $100 million mistake on a deal because of a misplaced comma. So their perceptions factor into how much they might use ChatGPT as part of their education. So as I said, talking about legal education in a little bit more detail. So when ChatGPT was first released, we had a lot of fun playing around with the model. We had it write exam questions, and it did fine, right? We had it write exam answers. It was also surprisingly good, and it was very cool to be playing around with it. We even had ChatGPT produce a syllabus, which it also produced a competent syllabus for a law class. Now, the bibliography was entirely made up, right? That was fun. So, is that impressive? I guess the answer depends, right? On the one hand, you could say generative AI, language models, right, is being trained on the answers, so perhaps it's not particularly impressive or surprising when programs pass a test on which they have been trained. right? Computers have been beating chess masters since 1997. On the other hand, right, it is impressive that my sixth grader could pass the bar exam even though most of what he knows about the law is wrong, right? So what have we seen in legal education and generative AI? On the spring exams, this is an exam period we completed in May, we found that as far as we could tell, so take this with a huge grain of salt, relatively few students cheated using the chatbot to write their exams or papers in their entirety, right? Students who used it were typically students who thought they were going to fail, right? And who thought this was going to allow them to pass. Now, why didn't everyone use it? Well, students are quite rational, right? The right answer matters in law. The error rate of the model is just too high for their level of what they're comfortable with. And so grades in law school are not, you get a high score, you get an A. Grades are curved. You're competing against your peers. If your peers do better, it doesn't matter if you got 90% of answers right. It's still a B+ if the rest of them got a 95. So the cost of error becomes more consequential when you're curving grades, when you want to do the best rather than just pass, right? Okay. So as I said, it might help poorly performing students, but students who studied are not going to blindly copy-paste text. Now, they might have used it to generate ideas. Frankly, if they did that, more power to them. They still had to filter and understand what's correct, what's not correct. In fact, we're currently debating a policy and what should we be doing with exam policy going forward. And what we're settling on is we might let students use ChatGPT for research purposes. Why? Well, we can't police it anyway, right? You can't catch someone who's properly edited an output. What are you going to do, right? We might permit that sort of thing for research purposes, but it can't copy-paste material, right? And frankly, as you read an exam, unless even when the entire thing was written by ChatGPT, you can tell because the model didn't sit in your classroom, right? Our exams are in the bar exam, which is administered to thousands of people. It's administered, drafted by the professor to the 20 kids who sat through the semester. Yes, you could feed the model the right sorts of information. That's not the model that our students have access to. Okay. There were students, so students may have used it, we're discussing this policy. Also, why weren't students using ChatGPT more? Well, because if they're intent on cheating, there's better ways to cheat, right? They can collaborate on exams. Most of our exams are take-home. They can ask a friend. There's ways to cheat that are very hard to detect that are just superior to chatbot. I'm not saying everyone is cheating. I'm saying those intent on cheating. There's perhaps more efficient ways to cheat on exams. Now, of course, legal education, it's not just exams, right? It seems likely that AI will disrupt education, is changing how it's done rather than displacing faculty or instruction, right? Now, for example, I do expect our faculty will change exams. In fact, I've spoken to several faculty who are thinking about how they want to draft exams, how they want to formalize assessments. They want to do more presentation, more oral arguments, fine. That's all good. But what you might be more interested in is also that faculty are now teaching different courses. In the fall semester, we had a class called Artificial Intelligence and the Law that over 100 students took. In the spring semester, we have at least 4, but I think there may be more classes, where faculty teaching students how to use generative AI effectively, how to draft prompts, and how to improve on their prompts to use them as part of their legal research as their sourcing material for a potential brief. Which does lead me to legal practice, right? You remember the prediction a year ago was that computers would start conducting legal research, drafting briefs in minutes, law firms would become obsolete, and it becomes clear that generative AI, and this is what Marinka referenced earlier, it's a booby trap for the unwary, right? It can be a godsend for someone who is a legal expert. It will cut down time drafting and doing research, so long as the legal expert will pay attention to the mistakes, will use it as a source of ideas, rather than this is the end-all be-all. Now, for real lawyering, open models are not particularly useful because, as we said, they make up facts and they make too many mistakes. Also, their mistakes are weird. and different from those that people make, which makes them relatively easy to identify. It also makes them particularly damaging, right? Want to know what happens when you use ChatGPT to come up with bogus sources to cite? You get slapped with Rule 11 sanctions. The guy's being disciplined by the by the New York Bar Association. He's not the only lawyer. There's other lawyers who've made the same mistake. These are serious career-ending or disrupting mistakes that people learn from mistakes and would rather not want to make them. Relatedly, right, all law firms, are they using AI a year later? So there was a survey conducted in September of this year, all various different US law firms. How many are incorporating generative AI in as part of their practice? Now, an aside, law firms have used artificial intelligence defined broadly for a very long time. LexisNexis, Westlaw, all of these are various different tools that have been used to enable them to make research. Generative AI would produce text rather than help them with research. Okay, are they using generative AI? 3% of law firms are currently incorporating generative AI in their law firm practices. 60% are not even considering it. So, are lawyers just conservative? Are we just boring? Sure, I think that can be true. There's a bigger problem here, which is the attorney-client privilege, okay? Using OpenAI, like ChatGPT in law practice, is malpractice, is professional malpractice. Putting confidential client information in the language model will waive attorney-client privilege, which means that information is discoverable. You may be forced to reveal it to a court when asked in a deposition. By revealing a communication to someone else, even inadvertently, right, will waive privilege. Let's say client consents. Yeah, sure, lawyer, you can use ChatGPT to do research. It'll be better. Doesn't matter. They've still waived privilege. Anything if they've talked to their counsel, that information is now discoverable. As I said, that is legal malpractice. So law firms have been experimenting, the ones that have sort of dipped their toes in it a little bit with closed models for research. But it doesn't really address privilege issues in law firms that have 800 attorneys, right? Privilege is personal, right? It's not firm-wide. So will models be developed to improve? Sure, particularly in cases that there's enough big bucks behind it that it's financially sensible to design a model that is tailored to a particular client. Broadly, not sure, right? Now, as is true with the technologies generally, their adoption is inevitable to some extent. What it does tend to do is, and here I'm going to venture into a little bit of a prediction, right? What's going to happen is, what I expect is it's going to reinforce existing market structure, not replace them or upend them, right? So why do I think that? Simple legal work, right? The things that people said ChatGPT could do, draft leases and non-disclosure agreements. Do you need ChatGPT to draft a lease? No, you just Google it. There's plenty of templates. In fact, the state of Maryland will provide you a sample template that you can use for a lease with all sorts of attachments. That stuff already exists, right? Lawyers that did this sort of stuff were replaced with the advent of the internet. Okay? So that's number one. Number two, so modern legal law firms, modern legal practice is hyper-specialized. It's really it digs down into the minutia, which is somewhat harder to replicate, right? Knowing the law also isn't heavily data-driven. You don't need to know every single case that has been decided on a particular question. You need to know what the precedent is. You need to know which court matters, what's been replaced. You don't need to know everything, unlike, say, in medicine, where it's really valuable to look at 10 to the 60th exponent of different molecules. You need to know a few cases. You need to appreciate where they fit. But it's not data heavy, right, as a discipline. Third, lawyers are not hired because they know law. Lawyers are hired because of attorney-client privilege. Lawyers are hired because of access and the networks to which they have access to. ChatGPT doesn't know anyone, right? So finally, I do expect generative AI to increase the divide between the haves and the have-nots, right? Good models, building a model, which I do expect will eventually happen, is expensive, right? Law firms that can build them, that have the resources to build them, can benefit, will improve their efficiency. It's going to be something that they might end up doing over time, but not right away. And so I do expect what's going to happen is what we've seen in the tech industry, in the tech sphere, where you have the big get bigger and the small just sort of get swallowed up by the rest with the advent of a new technology. This is not a democratizing tool. If anything, it's probably the opposite. So what am I afraid of? So my concern of open AI or generative AI models is the fact they don't know facts. They don't know the truth. Right? Law continues to care about factual accuracies. And so if generative AI disrupts legal practice to a point where it's agnostic to facts, that makes me really concerned. So I will end on this depressing note, and I welcome your questions.
So my name is Luka Pocivavsek. I'm a assistant professor in the Division of Vascular Surgery in the Department of Surgery at the University of Chicago. So Chicago's in the Midwest. As most of you guys know, University of Chicago is located on the south side, and we serve a fairly diverse patient population, mostly an underserved population since we're in the historic south side, which is largely African American. I work at our main hospital, which is about a 1,000-bed facility, and my primary practice is in aortic disease. I obtained an MD PhD at the University of Chicago with the PhD focus on soft condensed matter physics, and then took about 10 years to do training in general surgery and vascular surgery, and have now over the past 10 years integrated these and am trying to develop a surgeon-scientist lab. So clinically, I focus a lot on aortic dissection. So the aorta is the large pipe. So this is not fancy medicine. This is no immunogenics and such, but a lot of medicine in the end becomes a mechanics problem, right? So we walk around, be it from cancer or heart disease or whatever it is, what kills you in the end is there's some kind of breakdown of surfaces and interfaces that eventually become incompatible with life, and that leads to the end. One area where this can very nicely be kind of narrowed down to a mechanics problem is the aorta. So the aorta is the largest blood vessel in your body, carries blood from the heart. Let's see if this pointer does work. So it carries blood from the heart, which would sit right here, and then comes around. This is the ascending aorta, the aortic arch, gives off the blood vessels. They go up to your head and your arms. And then it turns south and carries blood to the rest of you, so your abdominal organs and your legs. It's a pressurized vessel, so like any pressurized vessel, the pipe in your house, if it undergoes failure, where the whole wall fractures, that's called aortic rupture, typically is incompatible with life unless you are able to get to the doctor very fast. And even in those situations, our ability to save the patient is fairly poor. I focus a lot on a partial fracture of the aorta, and we have a lot of this disease on the south side of Chicago because of poorly controlled blood pressure, and it's called an aortic dissection. So in an aortic dissection, what happens is that only part of the wall of the aorta tears, and that now fills with blood, and you have this double lumen situation. So Dr. DeBakey was the first one to identify aortic dissections and successfully surgically treat them down in Houston. And he focused on type 1 dissections, and I primarily focus on what's called a type B aortic dissection, which is the tear in the distal thoracic aorta. So how do we treat this? Let me start with a case example. So this is a patient of mine that presented, an 82-year-old, transferred from an outside hospital. So she presented like most aortic dissection patients. She came in hypertensive, blood pressure in the 200, with bad chest pain. And as we were talking earlier, in medicine, we were accumulating information in a massive amount. And the information I work with is extremely simple compared to some of the information you guys have heard about. I basically look at pictures, right? Pictures that are taken with x-rays. So a technology invented 100 years ago. But we make decisions on whether to take someone to the operating room or not, basically a life and death decision based upon this information. So here's the type of information that this woman comes with. So here's her heart. It's filled with a dye because we gave contrast to be able to enhance the contrast. Here's her ascending aorta, which looks okay, maybe a little dilated. And now here's her descending aorta. You see this flap in the middle, which is the crack. So here now is a reconstruction of this CT scan, which is the type of information that we can start to work with. So what can we do with this person? So one, we could say, okay, well, let's not do anything. Let's medically manage and, hope for the best, and perhaps she'll stabilize out. And that is how we manage most aortic dissections today. It is medical management, especially type Bs, unless they have impending rupture or malperfusion. And then we have to decide, right? The patient comes back, they keep getting scanned, the aorta grows. Everything we do pretty much in aortic management today, from clinical guidelines, depends on one thing and one thing only, which is size. But DeBakey already knew that size mattered, right, when it came to aortic disease. There's a lot more information here than just size, and that's a lot of my interest. So,
Dear Diary, today was good at surgery.
So 2 different ways of managing disease, of this particular disease, surgically. One is by, let me see if I can. One is through an open operation. So this is a video not of this patient, but another patient of mine. So this is the heart here. This is a thoracotomy. And here the aorta has been replaced by simply a plastic tube. Right? So again, this was invented by DeBakey. This operation is still routinely performed today, and it's a great operation, right? So this operation, I'll move it back a little bit. This operation functions extremely well, meaning if the patient can survive the operation, which is an important thing in balancing of what you do next, they can go home, and unless something else gets them, for 10 years, this is a stable repair. We've really shifted over the last 15 years in using endovascular technologies in repairing aortas. So here now, this is a fluoroscopy image, and if you watch on the bottom of the screen, you see this device being snaked up a wire. The wire is sitting in the left ventricle of the heart, and what this is the modern way of treating these diseases, or something we call TEVAR. So this is that particular patient whose CT scan I showed you. She underwent a TEVAR. Here's the stent that has been placed in her descending thoracic aorta. And the point of this is to try to exclude that false lumen or aneurysmal portion of the aorta, basically depressurize it. There's nothing very sophisticated here, right? In the open repair, we take the aneurysm out and replace it with a plastic tube. In this situation, we get a stent up there to try to depressurize that aneurysmal aorta, therefore potentially reducing the risk that that portion of the aorta ruptures. These are pictures of the inside in a model aorta of the deployment of this stent. Just gives you an idea of what this looks like. So here's this stent. It's covered with fabric. It's a large stent. When you typically talk to people, they think of stents that go in the heart. These are very small stents. This is a big stent. It can be 3 centimeters in diameter. It can be upwards to 20, 25 centimeters in length. So this thing will sit, as it does here, all the way from proximal aorta downwards. So what do we do? What's the problem with this particular approach? Because people would say, well, why does anyone still do the classic operation? With any technology, right, there's risks, there's benefits. Open operations, like the classic one that I showed you, the benefit is that you take all the risk up front. All the risk is taken during the actual operation and then the recovery from the operation. But once you survive that, the benefit is immense, right? You have no aneurysm anymore, and you can go forth with your life, at least as it concerns that particular pathology. The endovascular approaches, the risk is spread longitudinally. So there is a much smaller surgical risk up front. It's a much smaller hit physiologically to the body to undergo this endovascular procedure. The challenge is that these repairs ultimately fail, right? Or can ultimately fail. And the inability for the TVAR to work and exclude the aneurysm long-term leads to re-interventions and re-operations. So this is this is kind of a background. This is quite of a general audience. So what are the research questions that my lab has looked at? Have in particular been, how can we select patients using the plethora of imaging data that we're constantly accumulating on people from CT scans mostly, and that would allow us to say, okay, you truly would benefit from an endovascular approach or a minimally invasive approach, and your outcome is going to be good, right? Or this is not going to work for you, right? And even though you really want it to work for you and you don't want to undergo a large operation, if we do this, it's likely going to fail, and we're going to have another problem to deal with perhaps in 3 months and 6 months. So how can we harness the information we have? So my lab focuses quite a bit on using CT-based data from CT scans and essentially segmenting the aortas out, as you saw in that one scan, to create surfaces, and then harnessing the geometries of these surfaces to look at prediction models based upon outcomes using both clinical trial data and data from the University of Chicago cohorts, and being able to make these decisions. So the first thing to understand in being able to follow these models is aortas are basically bent cylinders, right? These are not very complex surfaces from a mathematical standpoint. I told you size is a criterion we use routinely and is in all of our guidelines. But changes in size occur normally as well. So this is 3 aortas, beginning with a 3-year-old child, extending upwards to a normal adult. And so size changes quite a lot. But one thing that stays constant is shape. So it's basically a bent cylinder. As disease evolves, the aortas can change size, and they do change size. But what your eyes should show you here, or hopefully everybody would appreciate, is that the shape of these things becomes quite odd, right? They become lumpy, they become distorted. So can you capture changes in shape in a quantitative way? If you go all the way back to the mid-50s in DeBakey's first paper on aortic dissections, he used really interesting language, right? He was looking at the chest open. He was visually looking at this structure, and words he uses there are idiosyncratically varying. I mean, it's a wonderful word because that's exactly what is being captured. Interestingly, though, for 60 plus years, the only thing we've used is size. So we have failed to find a quantitative parameter to be able to basically capture what DeBakey qualitatively was able to describe. The problem in medicine with qualitative descriptors is they're very difficult to implement in guidelines, right? People want numbers. So an open problem is, how do you quantify known qualities in changes in aortic shape? And this is what we've done, and this is basically harnessing differential geometry in describing surfaces. Again, none of this math is very sophisticated from a standpoint of implementation in computers, but what we do is calculate curvatures across the aortic surface and then map the aortic surface onto a Gauss map, which is a way of normalizing shape. And mathematicians have known how to do this for 150 years. With computers, it's quite implementable no matter how complex the shape is. And what we've discovered is that the key parameter that allows us to kind of differentiate aortic shape is this parameter delta K, which technically ends up being the fluctuations or the variance of the integrated Gaussian curvature across the aortic surface. So what we've discovered is a two-dimensional space. On the x-axis, you have inverse size. And we take the inverse purely from, it causes the data to be slightly more compressed and visual. But it's size on the x-axis, right? Which is the workhorse that has been used for decades. On the y-axis is our new shape parameter, this delta K value. And so looking at those same set of 8 segmentations, representative segmentations I showed you earlier, we can see that here's the child, slightly older patient, normal adult. And as we go up, we see that delta K changes very little in the normal patient population, all the way from a 3-year-old up to normal adults. And then as disease develops, there's a divergence in the delta K value, which is the signature we were looking for. How is this clinically usable? So here's the same data beyond the U of C cohorts. We've added a couple of trial groups that we've collaborated pretty closely with Gore, Endospan, and Medtronic. So again, you have size on the x-axis, shape on the y-axis. The greens are all the normal patients. There's no pathology, and you can see they're pretty much constant in delta K. The blues and the reds are patients that have aortic dissections. They all got treated using a TEVAR, which is the stent. We know the outcomes in these patients. We know who did well and who did poorly. The blues are all patients that had positive outcomes long term. The reds are patients that had poor outcomes long term. And so this allowed us to be able to basically run ML or logistic regression type analysis and say, can we predict the decision boundary as to when would a patient do well with this procedure versus not do well? So, we see 3 different classes. There's a group of patients where perhaps no surgery is best, right? You can medically manage them, give them antihypertensive, and then follow them, accumulate more data. There's a group at slightly higher delta K where TEVAR surgery has a high success rate, not only within the University of Chicago cohorts, but also these clinical trial cohorts. Then there's a group of patients that do not have a good outcome with TEVAR. So all of these patients underwent TEVAR because of a size criterion, but this information was not open to them at that time. These patients all did poorly. So these are patients that today we may say, well, open surgery, despite the upfront risk, may be something that would benefit you the most. We're extending this now from an AI standpoint to try to use simply imaging data. I told you here that outcomes were something that we retrospectively knew because we follow these patients. We're integrating sac volume, which has this aneurysm grown or shrunk after TEVAR, to allow the computer to have really an independent way of saying, is this repair working or is it not working? So with that, I'll end. I really would love to thank ASEF. I've had a wonderful experience with them. We had 2 students from ASEF so far, Žiga Donik from University of Maribor, a mechanical engineering PhD student who's done a tremendous job, and continuing to collaborate with him, and Janis Kramberger. And then this summer we hosted, he just graduated medical school now, also at the University of Maribor. So thank you so much. ASEF has been is really a great opportunity to work with Slovenian colleagues. Thank you.
Thank you for that. So I kindly invite Dr. Andrej Prsa, professor of astrophysics at Villanova University. His expertise in binary stars, extrasolar planets, and astrostatistics, did I say it correctly, is truly stellar. As we learn about using artificial intelligence to overcome computational bottlenecks in modeling eclipsing binary stars, you have to find something more like short for this. We are in for an astronomical treat. So that's our last. Thank you.
Thank you. Thank you for the invite. Thank you for such an awesome discussion. Let me before I go in, just a bit of personal reflection. We've heard from essentially all sectors that are using AI. I don't know about you, but I'm in the fundamental science, and I'm trying to figure out the basic properties of stars. Yet I had zero problem following each and every talk that was given today. And it's certainly because of the acuity of the speakers that came before me. It shows the passion for all of this stuff that I'm hoping to replicate as well. But the grander point that I'm trying to make is how similar our fields are, even though they are sciences apart. So I will give you yet another example of where AI is truly transformative. So I'm a professor at Villanova. Please look me up if you want to talk to me about anything. I came as a postdoc in 2006 for 1 year, and that year still lasts. So we'll see how long that'll last. So, yeah, of course, the laser pointer won't work here. So stars are far, right? And let me try to demonstrate just how far. Now, I'm a professor. I have to ask you guys questions. So we have to make this a little interactive. Let me ask you a quick question. So if you look out into the sky and you're not plagued by light pollution, what do you think? How many stars can you see with a naked eye? Just a ballpark. Is it 100, 1,000, 10,000, 100,000, or 1,000,000? Good. So the actual answer, if you have a pure moonless sky with nothing else, it's about 4,000. 4,000 stars that you can see with your naked eye. That's what I'm showing you here. All around, about 4,000 stars. Now you put a telescope on and so on. Yes, our galaxy, for example, has about 200 billion stars. So a few, right? My job is to measure those stars. My job is to provide the masses and the radii to the entire astronomical community. So how do we do that? Let me try to explain the size of the universe in something that you can wrap your minds around. Because if I start to talk about light years and so on, yeah, sure, but nobody will really, I think, follow what I'm trying to say. So imagine the sun the size of a basketball. I'm using metric units here, so apologies to my fellow Americans who are used to imperial system. If you need a conversion, ask me. I'm happy to provide that. But in science, we use metric for really good reasons. So imagine the sun being the size of a basketball, right? Then Earth would be the size of a pinhead, all right? Orbiting at a distance matching the width of 3 volleyball courts. I tried to put something together, but honestly, imagine a basketball right over there, then our little pinhead would be all the way out there past well, does anybody know what the length of this room is? Boštjan? About 25 meters? Let's say 25 meters. So we're in the ballpark. So that's how far our little pinhead would be. Now, Proxima is the nearest star to the sun, or to us past the sun. All right? It would be the size of a ping pong ball. From DC, I actually did this calculation for the preparation of this. You guys care to know where that would be? In Hawaii. Everything in between us, sorry guys, space is vast and pretty empty. So that ping pong ball would be in Hawaii. It would appear, if you had a strand of hair, it would be 20,000 times thinner than a single strand of hair. Or, if you want to think of it differently, if I had a quarter, an actual coin, in Los Angeles, from DC, that's the size, the angular size, that I would see the nearest star to us. So you would probably agree with me that it's not trivial to resolve a quarter from DC if you're trying to see it in Los Angeles, right? My point is Proxima is the nearest star past the sun, the nearest one. All other 200 billion stars, -1, -2 if I count the sun, are farther away. So yeah, stars are far. Have I convinced you of that? Good. Because my next point is then, well, how do you measure stellar masses and radii? You need to measure something that's a quarter size in Los Angeles that you're observing from DC, right? Well, my answer is with difficulty, right? Not too easy. Unless that is, if we're very lucky. So let me explain what lucky means in this case. If you have a binary star instead of a single star, and by the way, would you believe me if I told you that about 60% of all stars out there are binary and not single? Another fun fact that will serve great at a cocktail hour. It is true. The majority of the stars out there, stars like the sun and more massive, are actually more likely to be found in binaries than in single stars. What I'm showing you here is that fortuitous case that I'm mentioning. If you are lucky enough that you have a binary star, so two stars revolving around the mutual center of mass, where the orbital plane is aligned with the plane of sight, this is what happens. If you're measuring, and I'm sorry for the camera, I do need to step away from the microphones. So I'll try to yell so that the microphones will pick me up. What I'm showing you here is how much light we get as a function of time. So when the stars are apart, we're seeing all of the light from both stars. But when one of the stars goes in front or behind of them, of the other, we see a dip. So a small dip when we have one star behind that's less luminous, and then a deeper when it's more luminous. And from the shape of this, it's probably clear to everybody, at least qualitatively, that from the duration of the eclipse, we can infer stellar radii. From the depths of the eclipse, we can infer the temperature difference or luminosity difference between the two stars. And from the laws of motion that have been known since Newton, we can infer the masses of the stars. Given the quarter size LA star being nearest to us, it probably comes as no surprise that this way is the way of getting this done. To show you what this looks like in real life, I'm showing you here the measured masses and the measured radii from eclipsing binary star models. You see these points? The uncertainties in the masses and the radii are smaller than the symbols that I'm showing you here. Now I want to compare this with the very best next method, which is interferometry, where you put a whole bunch of telescopes all around the world and pretend it's a single telescope. It's a viciously difficult thing to do. So all the solid points here, I'm plotting as open points here, and showing you the few nearest stars that we can actually resolve and try to figure out their sizes. And you see the error bars on them? That's why. So you may ask me, well, Andrej, but do we really care? Do we need this type of precision? Is it that important? Let me try to convince you that yes, it is. I'm showing you here luminosity, so how bright the star actually is, versus the mass of the star. Turns out that mass of the star is the one parameter to rule them all. If you've missed on that reference, go read Tolkien. You're looking at what this dispersion here is. And you can say, well, this dispersion likely is just the uncertainties in the measurement, right? Well, let me blow up just this part here to show you that now you will see the error bars. And you see that this dispersion is statistically significant. This statistical significance, if you don't have the accuracy in your data, means tough. you won't know what's causing this. Because we can discriminate, we now know that it's heavy metal abundance. How much of anything heavier than helium, that's what astronomers call heavy metals, is in there, and that's what drives the evolution of the star and everything else. So it's truly important. Now, I will also say it makes astronomers that do my type of work prone to alcoholism. Not because of what you might think, but because at each and every conference that we go to, we are everybody's best friends. Because we can deliver masses and radii for their favorite type of star. Because there's no other way to get the masses and the radii for those stars. They're just simply astronomically far away. Pun intended there. You guys with me? So that is why this is so important. So how do you go from observables to fundamental parameters? Everybody here had talked about the gist of how you get this done. You triangulate the model that you're trying to understand. Now, the premise when we were building this model that is one of the models of the de facto standards in our industry is that we want to be able to model a Ferrari eclipsing a UFO. I'm showing you we can totally do this, obviously. So we're looking from this side. Everything that's green is visible. Everything that's red is invisible. Everything that's blue is partly visible. And we can do this. If you want to know more about this, the model is called Phoebe, Physics of Eclipsing Binaries. And the website's over there, so you can check it out. But the point is that this is a complex model. It takes, say, of the order of 1 to 2 minutes to synthesize the observables that we then need to compare to actual observations. So observables versus observations, you tweak parameters, and a model has about 500 different parameters. That's how sophisticated it is. So you're trying to essentially finagle the description, the best description that you have, and that can, as you can imagine, take weeks. Enter AI. So how do we solve this computation runtime problem that we're facing? I had banked on someone before me explaining the actual structure of the neural network. Nobody has. So please bear with me, because let me ask a question. How mind-blowingly difficult do you think artificial intelligence is on a scale from 1 to 10? And I'm just going to say 9 or 10, hands up. How about 5 to 8, hands up. How about below 5? Super simple. Come on, people. Everybody who's actually doing AI, raise your hands. In a basic concept, please allow me this. I will take 2 minutes to explain AI, and you will understand it. So those of you who think it's 9 or 10, I'm sorry to disillusion you. We just use fancy names to make ourselves feel fancy. It's really nothing to it. You have some inputs. For example, your observables. Each of these inputs is an actual scalar number. You multiply each of these scalar numbers with an associated weight. So this is just a number times a number plus another number times a number. So you're essentially just adding all these up together. That you put onto what's called a hidden layer. So you're propagating this forward onto the hidden layer. This triangle only means that instead of taking an actual linear combination that I was just talking about, you actually put a nonlinear function here so that you can turn linear mapping into non-linear mapping. And you get another set of points here, all single numbers. You do that again, you get your output. The gist of a neural network where that training comes in is that what you get out here at first will be complete nonsense. You compare that to your observations, and you go back, and you correct all of these weights so that in the next iteration, you're going to get closer. And you're just doing this over and over again until, lo and behold, what you put in actually produces what you would expect to get out. That is the gist of a neural network. Now, convolutional neural networks are a little bit more difficult. Everything that you've heard here, the generative neural networks have finesse, but under the hood, this is the principle. So what do? We take the models. Each model, it takes about 2 minutes to synthesize. We get those synthesis results and put them through the neural network. These are light curves because they tell you how much light we get. These are radial velocity curves. That's a measure of the mass of the system. So these two are what we produce. And once trained, which takes a couple of weeks to train this network, instead of 2 minutes time that it takes for one forward model with an actual physical run, it takes about a microsecond. Because once you train the network, remember what I just told you. It is multiplication and addition, one single set of nonlinear functions, one more time that, and you're done. So in consequence, the forward model goes from 2 minutes to about, of the order, if I include input-output operations, 10 microseconds. So if you do the math, you will immediately see why this is truly revolutionizing our field. We were able to do, for example, one binary star in a month. Now, we'll be able to do a galaxy worth of them in a month. So the speed up is about 6 to 7 orders of magnitude. And at this point, you may think, well, 2 minutes doesn't sound like a lot, right? I can hang around for 2 minutes. Well, but if you do have to do it millions of times, it's a problem. Now, why do we have to do it millions of times? Well, if you manage to shave this off, that'd be cool. But why do we need to do this? This is the last slide and the last graph that I want you to focus on. You need to explore the uniqueness of your solution. So if I tell you what the mass and the radius is, you should not take my word for it. You should ask me, well, how do you know what your precision is? And this is how do we know. So I'm showing you here several of the most principal parameters that we have. And these are the cross sections, and the diagonals here are the Gaussians that explain the most, what's called the posterior probability density, but ultimately it tells you how probable your values are. And what you're seeing here in two colors is red and green coming out of the model that took 2 weeks on a supercomputer, and what came out of my laptop in about 2 seconds, more or less. And what you're seeing is effectively indistinguishable results. So in consequence, this truly is transforming our field. And we managed to even convince NASA to fund us for this. So we now have a 3-year project that's happening because of this. So with that, let me conclude. Yeah, so just to show you, essentially, that we go from 2 weeks to 10 seconds. And finally, solicit any questions. Thank you.
So what are the next open problems that you're facing?
The biggest open problem right now is, so what I've just shown you here is a small part of the dynamical space. So parameters that fit, let's say, canonical binary stars. So if you want to apply this to any binary star out there, binarity does not discriminate against any type of star in there. And stars come in all shapes or forms. So in order to be able to simulate everything, the physical model that underlies the neural network has to be exceptionally well calibrated. So our job is to exceptionally well calibrate the model that so that it works as generally as possible. So I would argue that our job for the next 3 years is to achieve that.
So are these stars in our galaxy that you're processing? Everything is in our galaxy?
No, it is not. So our galaxy is practical because it's nearby. And by nearby, you understand that I don't really mean it when I say that. But there are trillions of galaxies in our universe, in the visible universe. So out of the trillions of galaxies, each of them with 200 billion stars each, we can find binaries that are the most luminous, arguably, but we can find them in other galaxies as well. And if they're eclipsing, there's no difference for us. Our uncertainties are not plagued by the distance at all. For as long as you can find them and figure out from their light curve and radial velocity curve morphology what the basic parameters are, you're off to the races. There's nothing indicating you against those. And in fact, one thing I've not mentioned, but might be worth mentioning, is that eclipsing binaries are also phenomenal distance scale calibrators. We can get distances from them just by measuring how luminous they are and measuring how bright we see them. That obviously has to do with the distance. So you can figure out the distance, thus you can figure out what the distance to these galaxies is. And that's routinely done.
And that's a good closure. Thank you for that.
All right.
I feel a lot of gratitude, and I think the right word would be I feel proud, or for everyone and everything you are doing, and also really happy that this event went through live and that we are all here. I would like to leave us all with a question. If we are back in Slovenia, where we return, able to really provide this kind of future minds, and to all of you in our homeland to live in this kind of intellectual totality, so be really able to freely and wholly express cultural, political, but also intellectual abilities and desires. And let's say to the ones that in a way we kind of lost, try to forge a really strong partnership, as we at ASEF are really striving for, to have and search for each and every one that is also beyond our borders to still contribute to our society and to our nation. I really thank you all, and I kindly invite Ambassador, the floor is yours for closing remarks and invitation to what is following. Thank you, and thank you all.
I found this symposium extremely and intellectually challenging, I would say. Many things are there that pretty much I did not understand well. But I know one thing. We Slovenians, we are really small but a great nation, I would say. Such a knowledge concentrated just in this room. I'm really astonished about it. We don't have just sportsmen here, which are exceptional in the United States. Obviously, we have this exceptional brain. And I feel honored on one side, and the other side, I feel so sorry that you are not back home. Meaning we would be able then to change some things in, let's say, in Slovenia. For example, instead of speed and the mass of stars, we would be able to predict the political behavior, for example, of the political partners, or how close they are to certain solution, or how distant they are, and who can form the coalition government, or other things that we might be faced with in the future, as I saw from some gaming predictions here. So we are in front of big and great challenges, probably, for mankind, as I said in the beginning, which is great. But on the other side, of course, these new technologies brings a lot of, let's say, also problematic stuff. and probably you are more on a positive way, then we come and we scratch the head and we say, wow, how many problems we have to resolve, especially in the diplomacy, in the international relations, which artificial intelligence cannot help us, and that's why we are here. I'm extremely grateful to all of you that you've been to us. I'm extremely grateful to ASEF as well. I think you are doing a good, really good job to connect people. Let's hope you won't be like Nokia. Nokia connected people, but then they had problems. Now they are back. Let's say you are constantly in. I'm really very, very satisfied with this outcome of today. Hoping at the same time that we will be able to repeat it. Now, Andrej asked what's the measurement of this nice space. I have to tell you that we finished it practically hours before the event happening, because there is a complete new flooring, and we are renovating the whole embassy upstairs and even upstairs. I think even in our renovation work, artificial intelligence would be of benefit. Then we would know when we will finish the works. You know, they were supposed to be finished in September. Now we are in December and still going on. Anyway, I would like to invite you all to a reception, to mingle among us, to chat, and let's say meet together in the near future and stand by, all of you with us and we with you. Thank you very much for all of that.